All right, so this is LeetCode 167. It's called toSum2. This is basically building up on toSum number 1 right here, but in this case, the input array is sorted. Okay, so we're given in one indexed array of integers. It's called numbers that is already sorted in non-decreasing order. I'm not sure really why they say this. It just basically means that it's an increasing order. And then they want us to find two numbers such that they add up to a specific target number. And they want those numbers to follow this certain rule. So basically they want it to be where index 1 is greater than 1, greater than or equal to 1, so it can be inclusive. But then they also, this is kind of the big part here, that they want it so that index 1 is less than index 2 and not inclusive. So this means that you can't use the same index. You can't use the same value, basically, at the same position. They want us to return the indices of the two numbers added by 1 as an integer array like this, of length 2. And then they say that there's exactly one solution and you may not use the same element twice. So going back to what this less than sign really means. And then they say your solution must only use constant extra space. So they want us to have a solution that uses this space here, constant, so that we're not using any extra space. Yeah, so let's go and look at the examples. Okay, so here's example 1. Our target is 9, and they want us to return an index. They want us to return an array of indexes of the numbers that add up to our target. So 2 and 7 add up to our target, right? Gives us 9. And for some reason in this problem, they threw a wrench at us, and the array starts at 1. The indexes, these are the indexes up here, 1, 2, 3, 4. Typically, arrays start with 0, or just anything in computer science usually starts at 0, but it starts at 1 for this example for some reason. And so that's why we would return 1 and 2, because 2 and 7 are the numbers that add up to 9. Cool. And then we notice that these are at different positions, so it follows our constraints above. Okay, just for sake of example, let's look at example 2. Target 6, we would return these two values because they add up to 6, right? And they're at different indexes, and this index is less than that index, which happens to be 1. It's less than 3, the index, the position, right? So it meets our constraints, so we can do that. Okay, so let's go ahead and talk about how we can actually do this. So typically, not all the time, but typically, whenever you get a problem that has some sort of sorted array or sorted kind of, I guess, yeah, like an array or something like that, they're almost always leading you to doing something with kind of almost like a binary search type of approach. You want to use the fact that it's sorted to your advantage. So we're not going to completely do the binary search approach, but we're going to use some of the same concepts. So I think it would be good to watch the binary search video I made earlier on this. But basically, I think like the naive solution would be to have a pointer here and then just look at the rest of the array, right? And say, do we find a value? In this case, we find it right away, but imagine this 7 wasn't here. Imagine this was like 8 and our 7 was over here. Then we'd have to search the whole array to find our values, and we'd have to do that for every value. So that time complexity would be big O of n squared, I believe, because you'd have to have like 2 nested loops to do this process. Okay. You could use one with You can do it using like maybe like a hash map as well, which is kind of how I think what the solution to 2sum uses, but it says that we want to use constant space, so they want us to not use any extra memory, basically. So what can we do? Actually, let's just go ahead and leave that back there. What can we do to make it so that we improve on this O of n squared solution? Basically, we have to leverage the fact that it's sorted. So if we leverage the fact that it's sorted, we can, and if you're familiar with binary search, usually use like a left and a right pointer. We can have a left and a right pointer, and let me blow this up a little bit so you can see this a little better. I think I'm gonna have to adjust it because all my writings went out. So we gotta, you know what, actually, I'm not gonna do it like that because I'm gonna leave it like that while I code it. So just go back. Okay, so looking at example 1, we have a left and right pointer, right? This is R for right. What we're going to do is we're going to calculate the sum at that point. So 15 plus 2 is 17, right? And how does that compare to our target? 17 is obviously greater than 9. So since we know that it's sorted, what we can do is just move the right pointer over to the left, because we know that every value to the right of this right pointer, if there were any other values, would just be bigger. So there's no point in just moving this over here if we know that we're just going to get a bigger sum. So we can just move it to the left so that we know we can get a smaller sum, because we need to eventually get, if we're already bigger than the target, we need to make that sum smaller. So we would move the right value over to the left, right? Okay. 2 plus 11, what does that give us? That gives us 13. That's still, we're 13 is greater than 9, so we do the same situation where we move the right pointer over. And you see this whole algorithm depends on the fact that our input array is sorted. Because if it wasn't, then we wouldn't be able to rely on that the values to the left of our right pointer are going to be smaller, right? So then now we get left and right, we get 2 plus 7, which is 9. 2 plus 7 is 9, right? And that gives us our output, and we can just return these values. And that was, this process would give us a time complexity of big O of n, because our left and right pointers only have to touch each element once. They don't cross each other, right? At this point they would stop, because we can't use the same element twice at the same position twice. So our time complexity would be big O of n, and then because we're just using 2 variables or 2 pointers, we're not using any extra space, so we're using constant space, so that would be fine. And yeah, and that gives us our solution. So we're gonna use this approach. I hope that made some sense. I'm gonna try to make this a little smaller. How do I do this? There we go. Okay. Yeah, so this completely improved our solution from being O of n squared here, all the way down to being O of n time complexity, but also with our space being O of 1. So that meets the constraints. Okay, so let's delete that. Okay, so we're going to need a left and a right pointer, right? So we're going to need a left pointer, which is going to be equal to, left is equal to, let's just write it out explicitly. Left pointer is equal to 0, right? It's going to start at the beginning of the array, how we did here. It'll be at the beginning, and then over here, right is going to be at the end of the array. So right pointer is equal to length of numbers, but as you know, the length of the numbers is always 1 more than the last index, so you have to subtract it by 1, because in Python or many other programming languages, the arrays start counting from 0, so we have to subtract 1 to get that last index, so this isn't out of bounds. Okay, and then pretty much just like the binary search approach, we're going to do while left is less than right, but we're not gonna do inclusive. It's just going to be while left pointer does not or is less than right pointer, and we're not going to have the or equals to, because it says here that we can't. You may not use the same element twice, so getting rid of having this would violate that that rule. So we're gonna get rid of this. Okay, while left pointer is less than right pointer, what we're gonna do is we're gonna calculate our sum. So we're gonna say sum. Oh, that means that's a keyword. So current sum is equal to numbers of, and then we're going to use the Python indexing. We're going to do a left pointer. So actually we could, to make this a little easier to understand, we'll just do it in variables. So we're going to say left value is equal to numbers of left pointer, and then we can say right value is equal to numbers of, instead of left pointer, we're going to do right pointer. So this is just preference, really. You don't have to do it like this. You can do it all in one line, but to make it so that we know what these variables come out to be, we can just do it that way. Left value. I think it's just a little easier so that afterwards you can read it a little easier. Okay, and then that's what our current sum is actually at that point. This is basically us adding whatever values are at the current index in that array. So in the first iteration, it'd be 2 plus 15, which is, this would come out to be 17 if we were running it with this input, right? And then we're going to have some if statements. We're going to say if current sum is greater than target, then we're going to say, in that instance, we want to move our right pointer, right? We want to do a right pointer is minus equals 1, right? We're just going to decrement it by one value. And then we're going to have an else if current sum, in the other situation where current sum is less than target, then we're going to say left pointer, we want to increment our left pointer, so plus equals 1. We didn't go over that in this situation here, but say that our target value was like, I don't know, 15 or something like that, or let's think of a bigger number. Say it was like 20. Then we would want to, and when we add 2 plus 15, we get 17, right? And 17 is less than 20. Say this is our target. Then we would, instead of wanting to move our right pointer to the left, we would want to move our left pointer to the right, so we'd get a greater sum in the and it would be closer to the chance of getting to 20. If that makes sense. So in this instance, we would increment our left pointer, and then otherwise else, this is in the situation where our current sum is equal to target. So if the code gets to this point, we know that our current sum is equal to target, so we can just return what they want us to return, right? They want us to return an array of the indexes of the values that added up to our current sum. So we're going to say return left pointer and then comma right pointer. This is how you can return an array. And then there's one small thing that they kind of threw in the mix, is that it starts from index 1. For some reason, this, like the problem that they're given, they're saying that it starts from index 1. So we would just add 1 to these values. Honestly, that's just kind of like a trick, I think, that they trying to see if we can catch it. Yeah, so let's see if this works. So if I made any errors. Cool. So yeah, that's it. Like I said, this is an O of n time complexity This is the time. And then the space is O of 1. It's constant. Even though we are using some variables, the thing that you have to remember is that these variables are not scaling as our input size grows. So as this numbers array, as it gets bigger, imagine that we have like an array of like maybe 5 values, right? And then we have like an array of like 1,000 values. No matter what, even if like 1,000,000 values, these left and right pointers, sure, we might use some integers. We might need some extra space like to represent a larger integer, but that's negligible. These values are gonna stay constant no matter the size of our input. So relatively so. You might use a little bit more bits to represent a bigger integer, but realistically, this is our space. So okay. I hope that made some sense, and thanks for watching.